lecture series is basically 10th in its series. So we are doing monthly lecture series under the umbrella of Indian Structural Health Monitoring Society. And today we are privileged to have Shri Sanjay Singh GAHARWAR, who is my senior colleague and very well respected personality in the field of structure health monitoring. And he has worked as a chief scientist and head bridge engineering and structures division of CSIR CRRI. He has more than 35 years of professional experience of research, consultancy, teaching, and field works, including planning, procurement, execution, and O&M, related to specifically bridges and structural engineering, including highways. So basically, he has a vast experience around bridges and highways, and he has authored 130 publications, including technical papers, reports at national and international levels. His research interests include quality assurance, distress diagnostics using injury and condition assessment, structural health monitoring, service life prediction, and rehabilitation of bridges and other structures. C&D waste utilization. He has worked a lot around this topic. UHPC, fatigue studies of bridges, performance evaluation of bearings, expansion joints, and shock transmission units. Additionally, he has also served as guest faculty at various institutes like IIHE, CIDC, and several academic institutions, including ACSIR. Sir, we all welcome you again for this on this forum and giving us your valuable time for this lecture. And I would also like to add, because I have worked with Sir for so many years now, and he has been instrumental in um, establishing the Asia's first expansion joint testing facility in CRRI, and that is a very prestigious project for all of us. And I'm sure it was not possible without you, sir. So that expansion joint facility basically is not available all over Asia. It is first time in India, which we are having. And now all the expansion joint which we were supposed to get tested outside India, now we can do in our CRRI because of sir sir's efforts. So he will be presenting a talk on optimization of asset management through structural health monitoring. I'm sure it will be a very interesting lecture, because I always enjoy sir's lecture, and we are all looking forward to hear you, sir. Over to you. Thank you so much.
Ma'am, first we should take the permission for recording, then we
So
can
yeah,
see.
sir, if you allow us, can we
Yeah,
record
yeah,
the
sure.
lecture if
Please,
that
please,
is okay?
please go ahead.
Thank you, sir. Yeah.
Shall I
Yes,
start?
sir.
Yeah.
Yes, sir.
So thank you, Dr. Naveed, for your kind words, and all the members and participants who are joining through online for this lecture. I'm thankful to Indian Structural Health Monitoring Society for giving me this opportunity. And topic Dr. Naveed has already mentioned. So this is the outline of my presentation. Definitely, I will start with the asset management, and slowly but surely I will be trickling down as shown in the slide. Now, the first major, you can say, what is the interest of all the stakeholders, and that is the infrastructure development. Infrastructure development, our country is very much in the limelight, and I think one of the I think second largest road infrastructure. We are involved in the development, and already we inherit a handsome amount of you can say infrastructure assets. Now, why it is necessary? It is trickling down to the transportation sectors, housing sectors, energy sectors, agriculture sectors, the sports sectors. So wherever you will see that, you'll find infrastructure. What are the benefits? Definitely the economic development of the country, very much that is there. Increased mobility, and of course the employment opportunity. That is a challenge not only in front of our country, but the whole world. But we are, by virtue of this enormous infrastructure development opportunities, we are definitely trying to solve our problems. And where lies the opportunities, there lies the challenges also. What are the challenges? Sustainability, as defined in the slide. I will not go word by word, but of course, the highlighting of that lower carbon and environmental footprints, protecting natural ecosystems, resilience, that is also upcoming challenges to changing climates, and of course, optimization of the utilization of natural ecosystems and their infrastructure services. So that natural resources, they are tending to deplete. So that also aspect we have to find out using that 3R. Coming to the asset management cost. Asset management, that is the topic for discussion today. And of course, it is connected with the structural health monitoring. So let us understand why it is related and how it is helpful. So these are the various stages of the asset development, starting with pre-feasibility, converting into feasibility reports, detailed project reports, and of course, planning for an infrastructure project. And once the micro level details they are designed and they are finalized, then a proper structural design, including aesthetics and other factors, sustainability and climate resilience, they are also accounted for. And then starts with the infrastructure, you can say, project through a proper procurement system. Once the construction of infrastructure is completed, there comes the operation and maintenance period. So this is the whole cycle of the asset development. Now, the whole life cycle cost, gone are the days when we were worried about the minimum initial cost. Now we are just seeing the whole life cycle cost, essentially consisting of initial cost plus O&M cost. Now, definitely, our resources, not only for our country, but the whole world, they are limited. And definitely, we have to think in terms of optimization. So this is the optimization equation. If we differentiate, keeping in view that once the construction of the infrastructure project is complete, then the whole cost involved in the construction can be considered as a, you can say, constant, including all those, you can say, the post construction arbitration and contract management issues. But still, if we take account for that, that is also a constant figure. And it is the, you can say, operation and maintenance cost, so which essentially depends upon the maintenance needs. So ultimately, when we differentiate it to find out the optimization, you can say, opportunities, or you can say the aspect, definitely long term, it is the O&M cost which has to be optimum. That whole idea is the asset management optimization. Coming to the operation and maintenance cost, how accurately the maintenance need can be predicted in advance, it is very much dependent on that. Now, there are two models. One model, when I say that maintenance need, definitely a new structure starts with the concept of design life. When we talk about bridges and flyovers, normal bridges and flyovers, now we are considering the design life of 120 years. Now, structure, environment, interaction, overloading, and so many other factors are there which essentially influence the life of the structure. And definitely the maintenance part comes. Hence, another terminology, service life, that is coming into picture. The effective service life, that is the period throughout which the structure which has been, you can say, uh, conceptualized, that fulfills its intended purpose. That is the, you can say, service life. So we are more worried about the service life, though we know that the design life, that is a assumptions and all the provisions we have taken in the beginning. So the first model is we go for assessing the maintenance need if the structure starts showing, you can say, the visible kind signs of distress. For example, cracks, spalling, corrosion of reinforcement. Then, and technology is available known as non-destructive testing, and I hope that each of you joining this webinar is very much familiar with that. But of course, science and technology has given us, you can say, the tools which are involved in the advancement of new and new techniques. So later on in my presentation, I will talk about what are the advancement in NDT, but this is the NDT. Second aspect is more challenging. And of course, when I say the optimization, that is the continuous monitoring of the response of the structure. So that leads to the structural health monitoring. This is the maintenance cycle. I have taken a asset, you can say, and the present graph, it shows that asset erode, but it is also very much, you can say, applicable to a bridge and flyover. You see, whenever the performance of an asset falls below a threshold, it essentially requires repairs, rehabilitation. And when the frequency, or you can say the duration, when the rehabilitation or repairs they are provided, its performance increases. But again, there are, you can say, thresholds beyond which we cannot go. So therefore, the options of replacement and upgradation, they are also available. So it all varies with the time, as I showed in the mathematical model of O&M cost. Straightforward, going to the structural health monitoring. You see, you are very much familiar with this. This is the ICU picture, and precisely here the one is a small baby where some sensors they have been put on different parts of the uh, body of the baby, and they are connected to the sensors. And on the other picture, you can say matured person is, of course, feeling similar type of experience, and they are also the pasted sensors, they are connected to the different instruments. And in one slide, the response, continuous response of these sensors, it is displayed. And of course, some, you can say, nurse is also, or doctor is also seen in the picture. And that is why it is intensive care unit. Some human intervention is always there. And of course, these apparatus which are involved in the continuous monitoring of taking data and showing it visually, and making, you can say, the doctors or the concerned persons who is taking care of the persons under consideration, the necessary precautions. So this is precisely the health monitoring. Now, if we give this analogy to the structure, here, this is the structure. Of course, the left hand side is the model, finite element model, and right hand side, that is the actual structures. So the analogy, if we apply, is sensors, they are installed in the body of a structure during its construction stage, and then a continuous system of making continuous record of the data of the installed sensors that is there. And probably the alarming signs or the response of the structure, whether it is performing as per the design assumptions or the assumptions made in the analysis, if the design is very typical, and they are there, and wherever some violations are there, then immediately the alarming stage, that is, you can say, very much known to the concerned authority well in advance. So that is precisely the thinking, thought process behind structural health monitoring. And this is one example, a real life example. Of course, it dates back to 2020, in November 2020, where the doctors in London, they came out, sorry, London researchers in USA, sorry, they came out with a, you can say, algorithm or technology or methodology they have developed, by virtue of which they were confident that they can predict the possibility of occurrence of a heart attack well in advance. So these are the media clippings. Just I have taken like that, just to show the utility of the health monitoring. So coming back to our structures, this is a picture I have shown. This is the analogy with the human body, and shown in the slide, foundation analogous to feet, ears, leg, bearings, knee and joints, reinforcement bones, so on and so forth, as shown in this slide. Straightforward going, why the structural health monitoring? I think by virtue of our previous slide, we everybody of us who is seeing this lecture or joining this webinar is convinced to some extent that structural health monitoring is useful. Now let us see how, going to the macro level details, what is the evolution of structural behavior with time and load, and of course the monitoring of the changes in the performance parameter of the structure. Nowadays, I think this Chenab bridge of Indian Railways, that is almost complete. And my friends who are joining this webinar, by virtue of their exposure to the media and newspaper reports, must be aware that this particular bridge is having a lot of typical design features. For example, even the earthquake spectra, that is also very typical and actually measured at the site by IIT Roorkee and one more agency that has been utilized in the design of this structure. Similarly, some blast analysis and you can say very high speed wind velocity 246 kilometer per hour. Even the blast, some portion of the, you can say, arch bridge get disturbed by virtue of some sabotaging activity. Then also the bridge is safe with a limited velocity of 30 kilometer per hour. So some such typical features are there which are not defined in the standards of IRC or BIS. Definitely, there we have to include this health monitoring system so that any change in the normal response of the structure, we get alarming situation or some sort of alarming signs well in advance so that the follow-up actions can be taken. Similarly, whenever a design is typical and we are not confident, engineers, they are not confident about the behavior of the structure, in that case also structural health monitoring is very much required. This is precisely the objective need for the performance monitoring, validation of the design assumptions, health of the structure, and pre-alarming warning system. This is very important. And optimum allocation of the rehabilitation resources, efficacy of the strengthening measures. There are certain rehabilitation schemes, say for example, external pre-stressing, where the natural, you can say, external pre-stressing is given against the action of, you can say, the dead loads, which is the natural, you can say, load. So therefore, we have to be extremely cautious. And whenever the implementation of any external pre-stressing scheme is there, the health monitoring, you can say, or the, you can say, response monitoring of that structure gives very much useful information, and it adds to the safety of the structure and effective implementation of that rehabilitation strategy. What are the performance parameters? Once we are convinced that structural health monitoring is also useful to structures which have their own language, which have their own, you can say, way of communicating with the humans. So these are the various performance parameters: strain, deflections or deformation, stress, tilt, vibrations, temperature, cracks, corrosion of reinforcement. In addition to that, list goes on and on as the design of the structure and the configuration of the structure becomes complex. So this I will take at the latter part of my presentation, where I shall be dealing with one real instrumentation scheme of a very recent bridge. What are the different techniques? What are the different sensors? I already mentioned about the performance factors, performance parameters, and definitely we have to look for what are the different technologies. Starting with a very old, you can say, the traditional electrical resistance based technology. Now, robust vibrating wire technology and fiber optic technology. And I am very pleased to see Dr. Naveed taking responsibility of coordinating this. And I also add that now she has taken the responsibility of propagating a new kind of technology, that is the piezoelectric sensor based technology for, you can say, structural health monitoring. So as the advancement is going on, new and new technologies, refinement, they are coming. And since my lecture is confined to the real life applications, I would like to share my experiences. So my experiences, or the my, you can say, the lecture, it has data based on excessively the use of vibrating wire technique. So I will be in detail deliberating this. So these are various electrical resistance. I think all of you are very much familiar. I will not go into the details as far as their working principles are concerned, they are very much based on the physics. Strain gauge, we have dealt at our graduation level, post graduation level, and even in the laboratory scale. So these are all the pictures of various electrical strain based, you can say, gadgets, sensors, and of course this is the data logger. Now, since the electrical strain gauge technology is very traditional, now there are more advanced version. So this is one still, wherever the need is of use and throw, means one time use of taking the real life measurements, then electrical strain gauge technology is still very much relevant. So these are the, you can say, limitations or precautions. For example, reconnections to be avoided, long length lead connections to be avoided, and for using concrete, a special protection device is required due to the fragile nature, and especially the rugged field conditions. Talking to the next technology, that is the vibrating wire strain gauge technology, vibrating wire based technology. And since it is very rigid and it has been extensively used in the decade 1990 to, I think, 2010, 2000, it was very much used. Even the 2000 to 2010 is still very much in use by virtue of its ruggedness. So this is the, you can say, strain gauge. Of course, the working on the principle of vibrating wire. I'm not going to detail. This is the how the gauge is installed. So the reinforcement bar in between, you see, with the help of some, you can say, setup, which remains inside the structure. Of course, I am talking about a condition where the possibility of installing sensors during the construction stage, that is available. So this is the gauge in place in between the reinforcement, and all these lead wires, they are coming out. This is the actual picture, a reinforcement gauge, and use the orange colored vibrating wire gauges, they are there. And of course, once the concreting is done, then they go inside the body of the concrete and they become a part of the structure, you see. And this cage protection, especially because the concrete is to be poured, so we have to protect those gauges. Their location, orientation, they do not get disturbed. The initial reading, while there's no concrete, waiting for concreting, that initial reading is taken. And of course, the post concreting, when the concrete is green, that reading also taken, and consistency has to be ensured. Now, this is the expertise of instrumentation. It is not just a matter of simply, you can say, the putting the strain gauge in between, you can say, reinforcement and tidying. It's not like that. Even after concreting, one has to ensure that the gauge is working. Of course, you may be having one idea of calibration. I will be discussing it later on. Let us see. This is another view, and these red colored wires, they are the lead. These are, you can say, the gauges, and tied, of course, a rosette in different directions, that is there. And of course, at that time, I'm talking about, you can say, since the 1990 to 2000 era, there was, you can say, in the initial stage, this was the small microprocessor based unit called as a readout unit. That is the reading, how it is getting displayed. Now it is obsolete. I will show the advanced system also. But you see the green lead, which is coming out. Now this is the data taker. Now all those green, blue, orange leads, they are connected to the sensors, and they are just coming out of the structure, and they are just going on where a proper junction box is there. So this is the data taker, where the proper positioning of the junction box was not there. That's why it is very much during the construction. It is like that. Now this is the proper junction box. Now this junction box is located inside the body of the structure. Now this particular case is belongs to a box girder bridge. That is why it is located inside the box. You are seeing the different leads coming out and getting attached to the data taker, which are positioned, permanently positioned in the junction box. Now, once this connection is over, then inside the junction box, it is through wired technology. So cables, they are there, and those cables, they are just facilitating these, you can say, the leads to come out of the box girder, and at the end of the you can say at one end of the you can say bridge, there is you can say the master computer that is there located in a particular safe place, robust place, where it is a perfectly safe environment for a computer, and they are attached to that. Now once that process is complete, the signals of the you can say various sensors, they may be transferred to a different location available any place inside our country through wireless technology. So that technology, level of technology has been increased, and now internet based technology that has taken place. That now advantage of vibrating wire technology, the degradation of the signals due to long length in the response of you can say the sensors, that is negligible. So that makes it very positive, or you can say the prominent these sensors to be used for rugged use, and initial shift is negligible. So this is very versatile, and that has been experienced also, well demonstrated. The next technology is the fiber optic you can say technology. Just showing the slides, not going into the details. You all know now, even these fiber optic sensors, they are cables everywhere. You'll find that these are there. So through this fiber optic technology, that is another way of connecting the sensors and getting the response of those sensors to the master computer room. So that is another technology. And then from there, it can be through wired or wireless. Generally, it is a wireless technology. It can be transferred to different places. But the drawback of this that, as compared to the vibrating wire technology, the optical fiber sensors, they are vulnerable to the, you can say, they are not as rugged as compared to the vibrating wire sensors. Hence, despite of you can say the popularity of optical fiber sensors, still the vibrating wire sensors, they are very much in use. There's another embedded type strain gauge vibrating wire technology. And of course, next question comes, if the opportunity of installing these sensors during the construction stage is over, then how can we fix that? The answer is yes. There's another weldable type of strain gauge. Of course, I was talking about the concrete. Now, this particular vibrating wire gauge can be attached to steel structures also. This again, uh, monitoring of the pre-stressing force using this optical fiber sensors. And this is further details. And this is the you can say the leveling sensors, water sensors, showing that. Of course, fiber optic sensors. And this is the temperature measurement, very much used. But of course, it's again the vibrating wire technology. You see the ruggedness of the sensors you can assess, seeing the shape of the sensors. This is the vibrating wire sensors inside the body, you can say, in between the reinforcement. Of course, this particular stage is means concreting is not done. This is thermocouple, very traditional. You know this. These are the temperature sensors. The green concrete is there, and you want to know what is the temperature, then these are there. And of course, the deflection monitoring. The N3 precision level, now at least it has become obsolete almost by virtue of you can say total station, and you can say the laser based high precision, you can say the level monitoring equipment. But still 90s 90 to 2000, this technology was very much 0.001 millimeter. That was the least count of that. And advantage, you can say the merits, self-supporting equipment, no human intervention is there, as well as the self-supporting staff, no human intervention. Hence the precision of you can say taking measurement was increased. This is the displacement transducers, LVDT. Still we use it. Coming to this again, the vibrating wire technology. This is the earth pressure sensors. Earth pressure sensors, I will show how during well foundations as well as the abutment, you can say the pressures, if you want to know, these are sensors which are used there. So this is one, you can say, pressure sensors used in the vicinity, you can say the reinforcement of the abutment. And this is the protection to be provided. Of course, this is the new construction, concreting is to be done as shown in the picture. This is the one, you can say, abutment position, retaining wall, you can say, and the vibrating wire pressure cells precisely. This is the location. So that once you know the theoretical shape of that, and it is the well demonstrated, almost well proven, but still you can fix up these vibrating wire pressure cells there. This is another tilt or slope. Of course, it's a stationary, you can say, tilt meter. But nowadays, that dynamic tilt meter, they are also very much available. It is based on this accelerometer technology. And this is the inclinometer sensors I will show in detail in the foundation, the case I will be taking. This is the sensors, and of course, a very long rigid wire, and again connected to a small, you can say, unit, readout unit. Now, this is the pictorial view, how this inclinometer sensors goes. This is the stemming of a well, and where this one cylindrical hole that is there, and of course a pipe, proper pipe is there, where a proper, you can say, sliding arrangement for the sensor, inclinometer sensor, that is there, so that the sensors can move inside that, you can say, slots. The cross section of that pipe is also shown, and it will measure, you can say, the tilt with respect to the vertical position. Now, this is precisely how it works. And this is the surface mounted vibrating wire strain gauge fixed inside the box girder. And this is a mechanical strain meter. And of course, again, a very high, you can say, least count. This is a crack detection device. And another view of that crack measurement based on vibrating wire sensor. And of course, corrosion, as I shown, one of the performance parameters. There are different, you can say, techniques: polarization, resistance, resistivity, open circuit potentials. Of course, the indirect measurement of corrosion in terms of chloride level measurements, and of course, the temperature measurement is also associated, supplemented, and these things. So this is one sensor which is fixed inside the body before concreting, and it works on polarization resistance. This is the junction box for that particular sensor. Coming to the dynamic measurements, now static measurements, they pose the limitation, and nowadays we cannot afford to stop the traffic passing over a bridge or flyover until unless a very emergency like situation is there. So therefore, the dynamic measurement in terms of this accelerometer, they are very much popular. Accelerometer, this is the cross section of that, and this is the whole, you can say, range of accelerometer shown over here in physical configuration. A load cell, again working on the principle of vibrating wire sensors, just to have that thing. Now this all family, piezoelectric sensors I am not covering. I think in some lecture Dr. Naveed, either she might have covered or she will cover that. Now, seeing these three technologies, and one more thing I would like to add, that since piezoelectric sensors, they are very advanced, and their trials, laboratory trials, they are very much in place. So their field trials, that is still a challenge. Probably it will take some time for those sensors to come to the to take up the challenge of field applications. Of course, the merit is that it can harvest the, you can say, electricity also. It is a self-sustaining, and no external electricity that is required, source is required. And of course, with respect to the sustainability, it is the promising sector of the future. But let us come back to our discussion, since the time is also limited. Seeing these technologies, electrical strain based, vibrating wire based, and these optical fiber sensor based, definitely the question comes into mind: what should be the criteria for selection of the sensors? Suitability for embedment in concrete, because concrete bridges and flyovers, they are also ample in number, and there is a competition between concrete and steel. So we cannot just ignore the concrete, which plays a, you can say, the one of the major role as far as the infrastructure projects are concerned. Long-term stability and degradation of the output signals, that is very important. Ultimately, what we are getting the signals of the various installed sensors. So let us take the example of a continuous bridge. And this is, you can say, the continuous bridge shown over here, typical, and the cross section. And of course, I think somewhere I was talking about before taking this. I will just put some a few words. Now, very first thing is the rigidness. Say, for example, we are working in a site conditions. They are not you can say the ready-made conditions. If we just bar the precast casting yard, and it's a cast in situ situation, so there definitely the rigidness of sensors or the whole system just transferring the data or the sensor response from the installed position leading to the master computer room and then further transferring it. So that situation rigidity is the criteria, and definitely that is one important parameter. Second one, you can see the output signal degradation. Suppose from master computer, if you want to further send these signals at a far away place where you can say the concerned stakeholder wants to see the data, then definitely this is very important. Long-term stability, vibrating wire sensor technology, they have proven 25 to 30 years. And once they are installed in a bridge, and the bridge is also stable, its condition is also relatively stable. Relatively stable means if you are providing the proper preventive maintenance, no major maintenance requirement is there, and definitely it will be a part of the structure, just like a reinforcement. So definitely the long-term stability, that is one of the important. If you compare this electrical strain gauges with this vibrating wire strain gauges, definitely there is no comparison. So here, when long-term stability is concerned, definitely the vibrating wire and gauge, they come in place. And optical fiber sensors, of course, they are also giving competition, but again, where the rough and tough conditions they are there with respect to the implementation of the project. Vibrating wire technology, it has an edge. Now, these are the various factors which are given due consideration, and of course, one important parameter is the cost. Nowadays, means people they have started thinking in terms of whole life cycle cost, but 90s to 2000, even the up to 2010, that was the scenario where the minimum initial cost that was dominant. And when you put the cost of instrumentation, that put a very small amount, additional amount, but again, people ask about the optimization of that cost. So the cost consideration is always there. How much money is available in your contract to provide the instrumentation? That's also a very important role in selecting the sensors, keeping in view deconsideration through all these factors. Now let us take a typical instrumentation scheme. So this is the well foundation. Of course, the features they are given over here, and this is the performance parameter: lateral soil pressure, longitudinal and hoop strain, tilt of well corrosion, for example. So how we will select it? Because as I mentioned that cost is also very important. So we should go for instrumentation, optimum number of sensors, so that it is a techno-economical proposal. So you see, this is one typical example showing the pressure cells and incremental casing. Another pressure cells there. You see the another view here, the rebar strain meters, they have been added. Why the increase in number of sensors? This I am talking about the well foundation. It is a very great depth from the you can say surface. So it is not possible to go inside again and again. Then the concerned stakeholder from the owning agency, or you can say contractor, if they have a doubt whether your installed sensor is working properly or not, I just take up this calibration before installing all these sensors inside the body of the structure. And of course, particularly in this well foundation, which is not accessible again and again once the concreting is done. And before installing all these sensors, we have to check the calibration, and we have to get it confirmed ourselves. And this is the second level. First level is from the you can say manufacturer's end. They also suggest you can say some test for the sensors, which will, if they pass through that test and are provided in their respective catalog, then only we proceed one step ahead. What are those? In second level, I will just mention. This is the superstructure optimum number of instrumentation position. It is shown over here. This is as far as the superstructure, you can say the span length. So where the prominent bending moment is there, we are taking, you can say, the instrumentation there. So this is one of the important parameters. This again, you see, now the vibrating wire temperature sensors, they have also been included. So once it is the question of a box girder, then what is the ambient temperature inside the box, as well as what is the ambient temperature outside the box, they are also prominent. So we have to put some optimum number of sensors for that also. What are the you can say the monitoring stages? So these are the different monitoring stages, starting with the evaluation, checking the calibration of the procured instrument, and then doing the calibration independently. And once we are getting satisfied, installing those sensors, again taking the initial reading, and then allowing the concreting. Once the concrete is poured, and our initial observations say that the sensor is behaving properly in terms of its output, you can say the reflected in terms of measurements, then we can go ahead during hardening, then the pre-stressing stages after the construction is complete. Then once the structure is in place, global response or load test, that is the acceptance test, or you can say the proof load test. Once this stage is over, then comes the O&M stage, where during peak summer and peak winter, we take this thing. What is the effect of light blow? If some overloading, you can say vulnerability is there, the time to time we can check that. And of course, this cycle may be continued on long-term basis, say following a frequency of 6 months or 1 year for continuous, you can say, number of years, so that we can have the data. Now, CRI has got a very rich experience. So these are the various, you can, some of the bridges on pan-India basis we have covered, is shown here. Ganga Bridge and Varasai. The story started, of course, from the Mandavik Bridge collapse 1980s, late 19, you can say 80s. That was the scenario, maybe 1989. And then the Ganga Bridge instrumentation 1990, new and old Mandavi Bridge. And of course, it dates back to, I think, 97, 98, or maybe 96, 95. This is the Thane Creek Bridge, 93, 94, the second Thane Creek Bridge. And this is the view under construction of the bridge. Where we install the sensors during the construction stage. These are the challenges of installing the sensors during construction stage. It is also very much similar, getting involved in the installation of the implementation of the project. And this is the Airoli Bridge view, and this is Loknayak Setu, Delhi. Zuari Bridge, where the external pre-stressing scheme was implemented and a load tests were performed, and we just monitor whether the load test is going, making use of that scheme or not. So this is the Ganga Bridge instrumentation. The colored, you can say, the well foundation, pier, and superstructure part, we were assigned to monitor this. I was talking about the second stage of calibration. Once the manufacturer has given, this is the, you can say, test as per the product catalog, then we formed, you can say, the concrete samples, and in the laboratory we performed, you can say, the preliminary tests. Say for example, if it's a strain gauge, we checked it using, you can say, the universal testing machine, whether the strain is proper or not. This is the same situation for temperature sensors as well as the earth pressure sensors. Now this is the response, you see, strain versus time. Once the instruments they are installed, it starts giving, you might have seen, you are seeing this king, that is the initial disturbance by virtue of, you can say, the movements during construction stage. And once the sensor is in place, then it is a, you can say, streamlined response. So this is another view, temperature rise. It says green concrete stage. You see the time duration after the concreting, how the temperature is increasing and then reaching to the maximum, getting settled down. Of course, different sensors following similar trends. And this is the ITO bridge. This is the instrumentation scheme adopted for, you can say, ITO bridge. You can see the vibrating wire longitudinal strain, and of course the transverse strain gauges, they were also installed. And this is the, once the instrumentation they were in place, and these are the response of various installed strain gauges. similar patterns, no abnormal king, and giving faith that the installed equipments are performing in a, you can say, defined or anticipated manner. And this is the deflection profile during pre-stressing. It is simply supported configuration of ITO bridges there, and different stages of pre-stressing. The simply supported is done by virtue of a different stage of pre-stressing getting hogged up. So this is the phenomena known only through instrumentation. The theoretical concept, it is difficult, not given in the, you can say, the books. And this is another view of the sensors, installed sensors, another view. And this is the instrumentation scheme for temperature. You see, optimum number, it's a techno-economical, you can say, challenge. Optimum number of sensors so that precisely we get the temperature profile. When the project was started, this IRC temperature gradient, that provision was not there. So these are the temperature sensors. I'll show the output, and I will also mention how this IRC temperature profile came into our standards. This is all the response of the different sensors. And this is the temperature measurement. You see peak winter and peak summer. You see the box girder, right hand side, you can see the differential temperature gradient. That is the typical challenge of the box girder span. That's a major consideration. Now here, I think it's a different. Ambient temperature is 13 degree. Here, ambient temperature 37 degree. One is in peak summer, one in, you can say, peak winter. And of course, this is the design temperature gradient which came into our code IRC 62000. So by virtue of monitoring the temperature response of a number of bridges on pan-India basis, then this temperature profile was, you can say, idealized and was suggested for design purpose in the IRC code. So that is one great contribution of instrumentation of bridges. And this is the strain variation during peak summer, and of course at defined locations. You see the similar pattern of variation of the instrument that is giving the structure is behaving properly, the first impression. And this is the deformation due to the change in the temperature. You see the time variation starting with 1 hour and then going to different phases. And the profile is also, you see, hogging up and then sagging. This is the global response test we performed. I'm talking about the ITO bridge, final loading and unloading that is there. This is the variation during the global response test. You see the underloading, onloading, the strain values. Plus is compression, minus is tension. And this is, you can say, the Aurori bridge configuration. And this is the deflection profile on account of, you can say, the temperature variation. This is the Juari bridge where the external pre-stressing was done and load tests were performed. The colored one is the span under consideration where the instrumentation was done. And this was the response, deformation due to the change in the temperature. You see the configuration, it's a balanced cantilever sort of thing. So here, the simply supported span means with due rise in the temperature, it was a simply supported span getting hogged up. Whereas in balanced cantilever, this is, you can say, the response of the span. You see. This is precisely the span. Deformation due to the change in the temperature of the cantilever arms. And this is the strain variation again. I think in the Ganga Bridge, Varanasi, the typical strain showing idea of showing these slides to use that enormous data is collected. Even the visual display of continuous display of data is there. So how it gives the alarming. Sometimes I will show in the real life example, if some threshold they have been fixed. And I will conclude also here what we have done taking this data. This is another deflection of both the cantilever span of, you can say, the Juari bridge. This is the shrinkage specimen, one available in the references and textbook, the shrinkage model. This is the actual shrinkage model we studied during this. This is the creep study of the creep strain. And this is, I'm coming to the well foundation of the Ganga bridge. This is the outline, actual, you can say, the structural configuration of the well foundation. And of course, the instrumentation is scheme. This is the instrumentation scheme for well foundations, having you can say the different uh, sensors in terms of, you can say, the earth pressure sensors. They were there. This is the lateral earth pressure sensors at different levels. This is the history, and this is a variation around the well hoop stress, you can say. And during the flood, how the response changes. So that record was also available. And of course, this is the mathematical model, that finite element modeling that has to be done. This is the comparison between the field values as well as the uh, analytical values. Again, another view, comparison of the lateral earth pressure at different level. This is level 3. And this is the tilt of the well through incremental when the well was going down. These are all recorded. Another bridge we handled. This is the 6-lane drain over Palam drain, 2.3 kilometer long, where we installed. This is the structural configuration, of course, during the construction stage. And you can say the precast construction that was there. This is another story. Means in addition to the concrete bridges, CRI has also monitored a number of steel bridges also. And sometime during you can say the 19 late 90s and early 20s, Ministry of Railways, they were facing increased axle load problem. So they just approached this. So we monitored those steel bridges also. And this is the ITO bridge strain variation that is there. And ultimately, over a period of time, we monitored the response, and then we fixed the upper bound and lower bound, you can say, value. This is the uh, is level, upper and lower limits for the RL of the mid span. So these threshold we fixed. And when we are going after 6 months, we are just checking how much change with respect to these threshold. If it is within the threshold, it's okay. Fortunately, or you can say, I should not say fortunately, but the structure behaved properly. We did not find any, you can say, abnormal response during monitoring. And this is further advancement. And this is the model updating. Of course, this system is also there. I will show in the one slide. And this is first parallelly developing a finite element model and actual performing the field instrumentation and getting input to the field instrumentation, feeding that value of performance parameter, measured performance parameter, to update the finite element model and tuning it. And once the model is tuned, then no need of further going for field for getting the data. It is the tuned or updated finite element model which will give the response of the, you can say, the structure. So these are the further equipment, automated automatic target recognition, of course, a remote monitoring system. I was just talking about. It's a vibration recorder, data logger. Once I showed the traditional electrical stain based, you can say, daughter logger family. This is the latest one, and this is the bridge vane motion BDI system, the latest. I just mentioned the finite element updating. So that theory is used by this equipment. So this is the case study. We have done it. And ultimately, enormous data that is collected, and management of that data becomes very essential. So that is to be done only by using this bridge management system. So one database bridge management system, of course, the GIS environment Sarah has developed. These are some of the snapshots of that. And this is the, you can say, the conceptual development of the bridge management system, various modules, and of course the GIS environment. And these are the conclusions why we are doing. I will add to this, covering the latest development. I just mentioned this development of this design differential temperature gradient. That is a big contribution of instrumentation to our country, coming as a clause in IRC 6/2000. And of course, the segmental bridge construction on the basis of this measurement of the temperature, continuous monitoring, we suggested the various improvements in the curing methods. You know? Otherwise, they were not, you can say, very much common. They were not aware. The stakeholder was not aware, and they were resulting in the development of micro cracks. So that is great, you can say, contribution of that. As I promised, these are the advancement in terms of non-destructive testing. Now this ultimately leading to, again, the BIM, building information tool. And of course, Nowadays, the artificial intelligence that is replacing that software, so that is also there. And so many advanced gadgets as shown in this slide, they are there. Laser scanning technologies, close range photogrammetry, less and less human intervention. That is the theory which is going on, and developments are also going proportionately. Geophysical measurements for geotechnical investigations, lidar survey techniques, you can say, is there. Coming to the real life, you can say, instrumentation scheme. This is the signature bridge, Namaste, very much famous in the whole world. And participants who have joined this webinar, if they are not visited this site, I will recommend that they must visit to see the various typical features of this bridge. And of course, it having a very typical, you can say, different design features, asymmetrical cable stayed bridge. So these are the number of sensors layout where they have been installed in this pylon, in this, you can say, stay cables, and of course connections. You can say the in the where the bearings they are there, where the it is cable stay cables they are anchored, they are also there. In all, there are 171 temperatures. You can say total sensors are there. They are measuring the structural temperature, strain gauge. You can say the wind sensors, they are also there since it's like asymmetric cable stayed bridge. Accelerometers, they are also there because it is a seismic zone where this bridge is located. Seismic accelerometer are also there. Displacement transducer are also there. Of course, the inclinometer tilts, they were also there. Corrosion sensors are also there. And sophisticated cameras are also there. Traffic analyzer, traffic count, just to take care of this overloading, they are also there. And other electromagnetic sensors, they are also there. Now, this is the whole story I'm just telling you. One, you can say the data transmission. The data is coming to one master computer room, and that is in the very vicinity of the bridge, as is shown over here. And once it reaches to the master computer room, then it's a wireless technology, which is just sharing the data. And this is the dashboard of the user interface, where I believe that the stakeholders, they have deployed dedicated staff for continuous monitoring. And this, wherever the defined threshold they are crossed, immediately warning signals that are received, and they are taking care of where this, you can say, happening. Immediately they are coming over here. This is the cockpit of the user interface. You can say how the signals they are coming. And this is the graphical display of the recorded data, which is coming over here. And this is the live view functions, a real-time presentation of the measured data. Of course, the data processing and making it simple to facilitate the interpretation of the results. Now you see the enormous data, it is being collected. So this is another challenge, how to compile it, where to compile it. Large capacity, fast processing computers, they are required. And of course, the user or the stakeholder, he should access the web interface using a simple device like iPad. So that is also there. All these features, they have been provided in this real life advanced, you can say, structural health monitoring system. So this is all. With this, I come to this end. Before showing my last slide, I just go back to that Chenab bridge I left over there. If they have provided similar sensors as I showed the sensors used in this signature bridge, and there they have connected to the nearest railway station wherever any threshold, because it is not only located in a very seismically vulnerable areas, but also strategically importance area also, where the savage road activities there also cannot be ruled out. So any such thing if happens, immediately the information goes to the nearest railway station, and then they are capable of taking all the necessary questions. First of all, they tell there, you can say, the concerned department, and immediately they rush to the slide. So they are there. So this is the last slide. Thank you for your patient listening, and I am sure that you're all very knowledgeable. You must be having queries. We can interact we can. I will try to share. You can say uh, my views on that. So thank you very much.
Thank you so much, sir, for such a wonderful presentation. You started from the very basics and then you took us to its field application with such a detailed, comprehensive explanation for each and everything. And really, sir, I admire and adore CRI for working in the field of structural health monitoring since uh, I would say 1989. Like you said, you started work in the field of SHM. So I'm sure by that time, not many in world would have been doing structural health monitoring, and definitely, I'm sure nobody in India must have started at that time the work in the field of SHM. So I'm lucky that I'm working. I have worked with the seniors like you who have almost started structural health monitoring in India. And then you finally ended up your presentation by giving some glimpse of the SHM, which we are doing, not we, but it's been done in the signature bridge, which is definitely a new thing for all the participants.
We hold such talks every month. And if you want to join the Indian Society, Indian Structural Health Monitoring Society, you can just Google it and you can just go to the website and fill up the application form. Thank you very much.